Hello my esteemed viewers, welcome once more to my channel. In our last lecture series, we talked about Kirchhoff's laws. We introduced Kirchhoff's laws. We also looked at some problems involving Kirchhoff's laws, how to determine the current flowing in a circuit using Kirchhoff's laws. In this particular lecture series, we're going to look at some other problems involving Kirchhoff's laws also, just to build on the foundation laid in our previous lecture series. So in this particular problem, we have a circuit which is being displayed on the screen. We have a circuit comprising of some resistors. The whole circuit comprises of two separate loops. We'll call the first one loop A. So let's call this loop A. This is loop A. Let's call this loop B. On how we intend to find the currents I1, I2, and I3, the first thing to do is let us establish the points where we can apply Kirchhoff's current law. And if we check this figure, if we check all the points, we can see that at point B, we have some current entering and some leaving. How many currents are entering the junction? We have just one. That is I1. How many are leaving the junction? We have two. That is I2 and I3. So we say that is our solution. At point B, we say that Kirchhoff's current law, which is KCL, yields the following equation. At point B, we have I1, since we know that the sum of the current entering the junction is equal to the sum of the current leaving the junction, or the amount of current entering the junction is equivalent to the amount of current leaving that junction. So we say I1 is equivalent to I2 plus I3. We can label this equation 1. Then we go to loop A and apply Kirchhoff's voltage law. So for loop A, how do we apply Kirchhoff's voltage law? Remember, one of the rules, we'll first of all assign a direction of current flow. Assign an arbitrary direction of current flow. So I'm going to use a clockwise direction. So this is clockwise. Having assigned the arbitrary direction of current flow, I now take note of the signs for each potential drop. This is a cell where, since I chose this direction, my current is coming out from the positive terminal. So let me say for loop A, KVL gives us Kirchhoff's voltage law. We can say this is positive 10. Coming to this point, the potential drop, if we check the current passing through this 2 ohm resistor, is in the same direction. This is the direction I1 is in the same direction as the assigned direction we chose. So the potential drop here is going to be negative. So we say minus 2I1 then we come to this resistor here. Of course, we are moving in a clockwise manner. I2 is in the same direction as the assigned direction we choose for current. So the potential drop here will also be negative. So we have minus 4I2. Everything will sum to 0 because KVL tells us that the sum of the potential drop is equivalent to 0. Sum of the potential drop in a closed circuit or a closed loop is equivalent to 0. If we simplify this further, we can say minus 2I1 minus 4I2 is equal to minus 10. You can actually decide to multiply through by minus 1 since all of them carries, all the terms carry negative sign before them. But well, let's just leave it this way to avoid confusion. So let's call this equation 2. We move on to loop B. We also apply KVL to loop B. If we do that, next choose an arbitrary direction of current flow. I have chosen clockwise. If you check the potential drop, if you check I3 entering 6 ohm resistor, I3 is moving in the same direction as the arbitrary direction we chose. So the potential drop there will be negative. So we say minus 6I3 we come to this resistor, the 8 ohm resistor. The current that we pass through this 8 ohm resistor coming from this side is also I3. It's also I3. So the potential drop here, and you know I3 is coming this way. So of course I3 will assume this direction. So discover that I3 is also in the same direction as our assigned direction. So we say minus 8I3. So minus 8I3. Coming to this point, this is also negative. Sorry. The current coming through 4 ohm resistor is I2, and I2 is moving in the opposite direction of the assigned direction we choose. So the potential drop here is going to be positive. So we have plus 4I2. All equal to 0. Minus 6 minus 8 is minus 14. So say minus 14I3 plus 4I2 is equal to 0. Let's call this one equation 3. Now for equations 2 and 3, we are supposed to solve simultaneously, but then if you notice equation 2, we have unknowns as I1 and I2, but in equation 3, the unknowns are I3 and I2, so we can't proceed that way. So all we have to do, we have to make equation 2 and 3 similar in terms of the unknown. So looking at equation 1, we see that I1 is equal to I2 plus I3. What will be I3 from equation 1? Or if we look at equation 2, we can say, okay, let's substitute equation 1 into equation 2. So substitute equation 1 into, substitute equation 1 into equation 2. So we have that from equation 2, we now say minus 2 into I1 is I2 plus I3. So we say I2 plus I3 minus 4I2 equal to minus 10. We simplify further. This gives us minus 2I2 minus 2I3 minus 4I2 equal to minus 10. So that's minus 2I2 minus 4I2 is minus 6I2, then minus 2I3 equal to minus 10. We can call this equation 4. So we can now solve equations 2 and 4 simultaneously. Equations 3 and 4 simultaneously. So let us solve equations 3, is a short form, equations 3 and 4 simultaneously. So bringing them together, I have minus 14I3 plus 4I2 equal to 0, and minus 6I2 minus 2I3 equal to minus 10. So we can eliminate I3. We can solve this simultaneous equation by method of elimination. So if we eliminate I3, then if we want to eliminate I3, all we need to do, just ignore the signs in front of them. Work with just the coefficient of I3. So we can multiply equation 3 by 2 and multiply equation 4 by 14. So this will now give us the same value. So if we do that, let's say eliminating I3, multiply equation 3 by 2 and equation 4 by 14. So that if we do that, equation 3, if we multiply by 2, we have 8I2 minus 28I3 is equal to 0. We can call this equation 5. Also, when we multiply equation 4 by 14, we have that 14 times 6. So since there's negative sign, we say minus 84 I2 minus 28 I3 is equal to minus 140. Call this one equation 6. So if you subtract equation 6, subtract equation 6 from equation 5, So that we have 8 minus 84 will give us 92. We've now give us 8 plus 84, which is 92. So we say 92I2 is equal to 140. As a result, I2 will be equal to 140 over 92, which is equal to 1.52 ampere. Using I2, in equation 3 gives, so you have, this is equation 3 here. This is equation 3. So minus 14 I3 plus 4 into I2. I2 is 1.52, all equal to 0. So we have that minus 14 I3 plus 6.08 is equal to 0. So that 6.08 is equal to 14 I3. Therefore, I3 automatically becomes 6.08 all over 14. That gives us 0.43 ampere. So if you now recall equation 1, where we say I1 is equal to I2 plus I3. So we say I1 is equal to I2 is 1.52, which is 1.52 plus 0.43. So that I1 eventually gives us 1.95 ampere. So you can see how simple it is to solve or calculate the values of current in a circuit using Kirchhoff's laws. The answers are I1 equal to 1.95, I2 equal to 1.52 ampere, and I3 equal to 0.43 ampere. So let's take on another example. Here we have another example. Without wasting time, just apply Kirchhoff's current law first. Checking the circuit diagram, convenient point here we can apply Kirchhoff's law is point B. So we say at point B, KCL, which is an abbreviation for Kirchhoff's current law, KCL yields, remember, you must always recall that law. It says that the amount of current entering a junction or a node in a circuit is equivalent to the amount of current leaving that junction or node. So checking point B, we can see that I3 is entering, I1 is leaving, I2 is leaving. So it implies that I1 plus I2 is equal to I3. So we say I1 plus I2 is equal to I3. Call this equation 1. Then the next is to apply Kirchhoff's voltage law to each of the loops. Let's call this one loop A and call this one loop B. Having identified them as loops A and B, let us assign an arbitrary direction of current flow. I choose clockwise. You can choose anti-clockwise. You'll still get the same answer. So for this first circuit, we have that I1 is moving in the right. The direction we chose is to the left. So our arbitrary direction of current flow is opposite the current entering 4 ohm resistor. So the potential drop there is going to be positive. So we say for loop A, Kirchhoff's voltage law, which is KVL, gives 4I1. We move on to the next point. We can see that going this way, we are now moving in the same direction as I2 because this current I2 is what is passing through this 8 ohm resistor. So we say minus 8I2, since they are in the same direction, is equal to, minus, because we are now going this way, coming out from the negative terminal, so we say minus 12 equal to 0. That is 4I1 minus 8I2 is equal to 12. Call this one equation 2. Sorry, this is 2 volts. 2 volt, please. So this will be 2, not 12, please. And we move on to loop B. So for loop B, we can see that this is 10 volts. So since we are coming out from the positive terminal, we say that 10, see KVL gives us 10. We move around, we just have I1 entering the 4 ohm resistor. We have just one resistor corresponding to this circuit. So we have that 10 minus 4I1. Why did we say minus? Because we have chosen a clockwise direction and I1 is moving in the same direction as our assigned direction. So 10 minus 4I1 is equal to 0. See, this is quite easier than the previous example. We can easily find the value of I1. So here we can now say that 10 is equal to 4I1. Calling this one equation 3. So that I1 is equal to 10 all over 4. That gives us 2.5 ampere. If that is the case, using equation 2, we can obtain the value of I2. So we say 4I1, this is equation 2, take note. So we say 4I1, what is I1? 2.5 ampere minus 8i2 equal to 2. 2.5 times 4 is 10. So we say 10 minus 8i2 equal to 2. So that minus 8i2 is equal to 2 minus 10, which is what? Minus 8. So minus 8i2 is equal to minus 8, so that i2 is equal to minus 8 over minus 8. That gives us what? 1 ampere. So it implies that I2 is 1 ampere. Then, having obtained the values of I1 and I2, we can proceed to use equation 1 to find I3. So using equation 1, we have that I1 plus I2 is equal to I3. So that I1, we calculated it to be 2.5 ampere. I2 was calculated to be 1 ampere. So therefore, our I3 is equal to 3.5 ampere. So bringing all equations together, we can say I1 is equal to 2.5 ampere. I2 is equal to 1 ampere. And I3 is equal to 3.5 ampere. These are the answers to the problem. Like I said earlier, this particular question is much more easier than the first one. But then you can see how we have used Kirchhoff's laws to determine the currents I1, I2, and I3 in the circuit. So, on this note, I've come to the end of this particular lecture series. Remember to like my channel, subscribe to my channel for more notifications. Once new videos are dropped, you'll be notified once you subscribe to the channel. Remember to drop your comments at the comment section. There are issues you want us to handle, you can drop them at the comment section and you'll be promptly attended to. Thank you and have a nice time.